Alright, so very good evening to all of you. So I welcome you all on YouTube channel of Unacademy IIT JAM Live. This is your educator Srishti, and in this particular session we'll be discussing more questions on thermodynamics. Okay, so without further delay, let's start with the first question. So this is your first question right in front of your screen, and if you can hear me properly, if I'm audible, so just let me know in the comment section. So this is your first question. So, in this question, you have to identify the correct statement. Okay, so you have to find which statement is correct in these four options. Yes, so come on, everyone, just quickly tell me the correct options in this case. Okay. All right, great. So most of you are going with option B. So let's read this question. If the pressure of system is greater than pressure of surroundings, okay, then you have to figure out the correct statement, right? So now in these four options, basically, first statement is work is done on the systems by the surroundings, okay. So let's suppose this is our system, this one, okay, so this is our system and this one is the piston, okay. So pressure of system is basically greater than pressure of surroundings, okay. So pressure of system is greater than pressure of surroundings, okay. So definitely what is the case, expansion can take place, okay. If you see, let's suppose this is the V initial volume, and after this pressure, right, because it's greater than your surroundings pressure, so V final will be this, okay. Now if I calculate delta V, so delta V will be definitely positive, okay. So if delta V is positive, this means this is the case of expansion, okay. And we know expansion type of work generally in chemistry is negative, okay. So it means work is done right on the surroundings by the system, right. So correct option is answer B, work is done on the surroundings by the system, okay. So third option is work done on the surroundings by the system is equal to work done on the surroundings by the system. This one is incorrect option, right. See, it can differ from, right, case to case, and then we have internal energy of the system increases, okay. So for this statement we need temperature, okay. And in this question, right, basically they are not just right taking temperature into consideration, so definitely option D is incorrect, okay. So correct answer is option B, work is done on the systems by the surrounding, okay. So I hope it's clear. Now let's go to the next question. So you can go with Maxwell square. Okay, so Maxwell square is the most important topic. So definitely there are right high chances that question will definitely come from Maxwell square. Alright, so okay, so let's see this question. Heat capacity of a species is independent of temperature, right? So we have four options. Now we know basically how we can calculate total degree of freedom or how we can calculate heat capacity, okay? It's the summation of heat capacity of translational motion plus rotational motion and plus vibrational motion, okay? So this is the thing. Now if it's independent on temperature, so definitely this vibrational motion is dependent on temperature, okay? So whenever we are taking heat capacity for monoatomic gases, generally we take only translational motion into consideration, okay? Generally we take only translational motion into consideration. So that's why the correct answer is option D, because for translational motion it's 3 by 2 r. Alright, and energy is 3 by 2 RT, right? If you want to calculate internal energy, so that is 3 by 2 RT for monoatomic gases, okay? So the correct answer for this question is option D, right? So is it clear to all of you? Any doubts in this question? For basically JAM, Joule Thomson and chemical potential numericals, okay? So the basic reading is enough from these two topics. From Joule Thomson you can just go with the signs and values for ideal gases and real gases, so that is important. And from chemical potential, just the definition and the Maxwell square, okay? How we can relate chemical potential and Gibbs free energy, so this part is important, okay? You don't have to go to numericals from these two topics, okay? Just the definition and derivations and how you can just derive a particular formula using two derivations, right? So this part is more than enough for from these two topics. All right, okay, so we have to find correct options, okay. Now option A is G is equals to H minus Ts. This is the first option. So definitely if I want to define, right, a function, okay, a general function, so A option is definitely correct, okay. We know G is equals to H minus Ts, okay. So A is definitely correct. Now if I want to define Gibbs free energy for a system, okay, so B is also correct, where G is for system, delta H value is also for system, and entropy is also defined for system, okay. So this option is absolutely correct. Delta G is equals to delta H minus T delta S, okay. Now if I go to third option, so let's suppose this is T delta S of system. If I'm taking this thing to LHS, okay, so this will be delta TH system, okay, just the rearrangement of the equation, okay, delta H minus delta G of system, okay. So this option is absolutely correct, okay. Is it clear to all of you? Next is delta G system is equals to delta G system minus T delta S, okay. Now if I'm taking this T delta S, so definitely there's a sign difference, okay. Delta H system is equals to minus T delta S minus delta G, right? So option D is incorrect. Option A, B and C is are basically incorrect options, okay. Right, okay. So you're definitely correct, Siddhant, that we cannot write the absolute values for these right equations, but basically this one is for your a system, okay. Let's suppose this is your MSQ question, so you can define this for system, okay. If we just find out the value, so we can just definitely write this as G, right? So it's a possibility that option A is absolutely correct, okay. All right then. So is it clear to all of you? Any doubts? See, we are taking system and surroundings into consideration. Okay, for A option, we are taking system and surroundings into consideration. So, if we are taking system and surroundings into consideration, so G is equals to H minus T delta S is possible. Okay, so we are taking integration of this total value. Okay, so we are finding the total value for system and surrounding. So, we can go with option A, right? Okay, so let's take the second question. If you are not clear, you can just definitely ask your doubts. See, let me just give you one example just to clarify your doubt, okay? See, let's suppose we have this system H is equals to U plus PV. Okay, we generally write this equation H is equals to U plus PV. Okay, now if I want to calculate the difference, okay, so what I write? I write delta H is equals to delta U plus delta PV. Okay, I hope this equation is clear to you. So we write delta H is equals to delta U plus delta of PV. Okay, now if I want to find out this difference, that is delta H or delta U, so how I can expand this equation? I can write H2 minus H1 is equals to U2 minus U1 plus P2 V2 minus P1 V1. Am I correct? Right? This is how I can write down this equation. H2 minus H1 is equals to U2 minus U1 plus P2 V2 minus P1 V1. Okay. Now this means this is nothing but summation of two equations. And what is that equation? H1 is equals to U1 plus P1 V1. H2 is equals to U2 plus P2 V2. Okay. Now there is existence of these two equations and we have to find the total change. So we are taking these two equations into consideration. Okay, so this thing is same with this equation, that is G is equals to H minus Ts. Okay, now if I want to find delta G is equals to delta H minus T delta S, so we generally take two equations into consideration, that is G1 is equals to H1 minus T delta S1 and G2 is equals to H2 minus T S2. Okay, so there is existence of G1 and G2, but it's a total value. Okay, we cannot find at this particular time, right? Because definitely energy is very difficult to calculate, but we are taking the total value. Okay, so it is definitely possible that there is existence of this G value. All right. Okay, is it clear now? Okay, so what about this question? All right, so wait a second. Okay, so how you can just think of option C, all of you? It's written isothermal, okay, and the formula is minus nr delta T. Is it possible? If the function, if the system is isothermal, so delta T must be zero, right? If it's zero, so work done is equals to zero. Is it possible that always work done is zero for isothermal reversible process? Right? So definitely option C is incorrect. Can I say this thing? Option C is incorrect option. Okay, fine. So now let's discuss this question. So basically the question is, in which of the following cases the work done in an ideal gas system with constant moles N be represented by nr delta T? Okay. Next thing is, let's take first option. Okay, so isochoric reversible heating. So we know first law of thermodynamics. Basically, what is your work done? Okay, work done is minus P external V2 minus V1. Okay, so this is your work done. And in first option, isochoric reversible heating. Okay, isochoric means constant volume. So dV is equals to 0. If dV is 0, this means work done is equals to 0. But we have to get work done is equals to minus nr delta T. So that means option A is absolutely incorrect. Okay, let's go to third option, isothermal reversible expansion. Okay, right? So isothermal means dt is equals to 0. If dt is 0, so definitely what we can say, work done, okay, is not equals to minus nr delta t. If dt is 0, so we cannot write like this minus nr delta t, because dt is equals to 0, so you have to put 0 value over here. So work done will be 0, right? So option C is incorrect. Now you have to figure out between option B and option D. Okay, so in B option, the process is isobaric, right? So that means P external, or we can say dP is equals to 0. Okay, if dP is equals to 0, this means basically you are at constant pressure. Okay, so P external is fixed. Okay, P external is basically fixed. So what we can write down? We can write down W is equals to minus P external V2 minus V1, or we can write down minus P external delta V. Okay, so is this point clear to all of you? Now it's written in this question that it is for ideal gas. Okay, it is for an ideal gas. So we know for ideal gas PV is equals to nRT. Fine, PV is equals to nRT. Now if I take change of this equation, so delta PV, okay, delta PV, N is constant, R is constant, so NR delta T. Okay, delta PV is basically NR delta T, right? So what can I write? This is your constant value, P external is constant, so definitely P delta V is equals to nr delta t. Okay, so I can substitute this value from nr delta t, right? So now work done is minus nr delta t as required in this equation, right? So for isobaric reversible expansions, right, the correct answer is option B. Your work done is minus nr delta t, because for D option, adiabatic irreversible expansion, so this means minus P external dV. Okay, and it is irreversible first of all, right? So you cannot just convert this system to P internal is not equals to P external, so we cannot write PV is equals to nRT for irreversible expansion. Am I clear? Because in reversible expansion only P internal is equals to P external, so we can write ideal gas equation over here, right? But we cannot write ideal gas equation for irreversible expansion because P internal is not equals to P external, right? So correct answer over here is option B. Is it clear to all of you? Anyone who is facing doubt in this question? Just confirm it, okay? Because so that I can take the next slide, okay? All right then. Okay, so now let's take the next question. Okay, so what are your doubts? When pressure is constant, it means process is irreversible. See, let's take next question. Let's take previous question. So basically, when pressure is constant, this means process is irreversible. No, isobaric means basically your change is constant. Okay, so P external it will be fixed. Okay, P external is basically fixed. Okay, so let's suppose at time T internal, P external is 2 atm. Okay, so at time T2 interval, right, the P external will be 2 atm only. So this means you are working at constant pressure. Okay, next thing is with this isobaric you have reversible term. Okay, reversible means P internal is equals to P external. Let's suppose P external is 2 atm, so P internal will also be 2 atm. That means P external is equals to P internal, then only the system can be in reversible expansion. Okay, and for reversible system generally we use PV is equals to nRT, because now you can relate with the gas which is present inside the system. Okay, so now we are using this equation, PV is equals to nRT, right? So that's why we are going with P delta V is equals to nr delta t, right? So this thing is constant but it has some value. Okay, so this is your nr delta t. Fine. So isobaric doesn't mean that the system is basically irreversible. It means that P external is equals to 280 at T1 temperature, right? And let's suppose we are increasing the temperature or decreasing the temperature, the pressure will be same. Okay, you are working in constant pressure environment. Okay, but in irreversible cases, P internal is not is equals to P external, so we cannot relate PV is equals to nRT equation. Okay, so is it clear, Umesh and Bharti? Right, this expression is clear. Alright, so come on everyone, just give answer for this question. It's very easy. Just we have to apply basic equations. Alright, okay, so let's solve this question. So the question is the heat capacity of 10 mole of an ideal gas. So the system is basically ideal gas, okay, and number of moles is equals to 10 moles, okay, at certain temperature is basically 300 joules per Kelvin, okay. So heat capacity at constant pressure. So Cp is given to you, that is 300 joules per Kelvin, okay. The heat capacity of the same gas at the same temperature and at constant volume. So basically Cp is given and you have to calculate Cv. Right? You have to calculate Cv. Cp is given. Okay. Now see, we have very famous equation. Cp is minus Cv is equals to Nr. Okay, this is the equation. Now sometimes we get confused if we have to basically use n or not. Okay, so how you can just rectify your confusion, or how you can just clear your confusion, just see these units. Okay, Cp is joules per Kelvin and Nr, our unit is basically joule per Kelvin per mole. Okay, now if you have n over here, so you'll multiply mole, right? So mole and mole inverse would be cancelled out and you'll be left with joule per Kelvin. Okay, so here the unit is joule per Kelvin, and RH is also joule per Kelvin. Okay, so this means we have to use Cp minus Cv is equals to Nr. Okay, so now we have Cp value, that is 300 joule per Kelvin. It's always better thing to just solve the equations with help of your units. Okay, so minus Cv, you have to calculate Cv. is equals to NR. N is given 10 mole, okay, and R we have to use 8.314 joule per Kelvin per mole. Okay, now what's going to happen? Definitely you have all these values, you just have to find out Cp. So mole and mole inverse will be cancelled out, and joule and per Kelvin will be cancelled out with joule and joule per Kelvin. Okay, so you can find out this particular value. So now the value is Cv is basically right is equals to, you can just find out all these values and just tell me what value you're getting. Okay, so 300 minus 83.14. Okay, so this is going to be your Cv, joule per Kelvin. Okay, so is it clear to all of you? Any doubts? Is this thing clear? Just you have to do this calculations now. Okay, that Cv is equals to 300 minus 83.14. Okay, and this will give you somewhere around 300 minus 80 is basically right 220. So basically it will give you some value around 217 joule per Kelvin. Okay, so there is no need to just take your calculators. You can solve without calculators also. Roughly 300 minus 80 is 220. So the value is close to 220. Okay, and you have only one option that is close to 220, 217 joule per Kelvin. Okay, so this is how you have to solve this question. Okay, so let's take next question. Right, okay, so good work all of you. The correct answer is B. How? For the above Carnot cycle undergone by an ideal gas. Basically, this system is for your ideal gas, okay? Identify the process in which the change in internal energy is non-zero. Now, if change in internal energy, right? Okay, change in internal energy is basically not equals to zero. So this means the temperature change is not equal to zero, right? Because internal energy is definitely a function of temperature. Okay, so now if internal energy is non-zero, so temperature change should not be equals to zero, right? So now we know for isothermal conditions dt is equals to zero. Okay, dt is equals to 0 for this process and for this process. Okay, so we can cancel out 1 and third. Okay, so right, we can cancel out this option because we have first process, we can cancel out this option because we have first process, and we can cancel out option C because we have third process. Okay, so we can cancel out three options using this information, and only one option is left, that is option B. Okay, because in your adiabatic process the temperature change is not zero. Okay, the temperature change is basically non-zero, so that's why the correct answer is option B, second and 4. Okay, so I hope this one is clear. Okay, so we are getting basically mixed answers. Okay, B, C, and then B and C. Okay, so let's solve this question. So first of all, what you have to find out, I indicate which one of the following relations is not correct. Okay, so you have to find the false relationship. Okay, so let's go with first option. So first option is basically right. See, first option is dt by dv at constant entropy. So dt by dv at constant entropy, this is the direction. Okay, dt by dv at constant entropy. So basically your base is internal energy, right? So this is the direction in which you are moving, right? So definitely your base is internal energy. So we'll start from pressure. Okay, so dp by ds at constant volume, dp by ds at constant volume. Okay, so this part is correct. Now let's find out the sign of this right reaction. So next is we are going in upwards direction, and here we are coming downwards. Okay, so sign is opposite, so that means option A is absolutely correct. Okay, option A is absolutely correct. Now let's go to option B. So dt by dp at constant entropy. Okay, dt by dp at constant entropy, fine. dt by ds at constant pressure. Okay, next is we are heading towards your enthalpy. Okay, so next is dt by ds at constant pressure. Okay, so we'll start from here. dv by ds at constant pressure, so definitely this equation is incorrect. Okay, option B is incorrect. So there is no way to find this relation because it's dt by ds. Okay, so they are diagonally opposite to each other, so there's no way to find out this relation. Okay, so option B is incorrect. Now let's go to third option. So ds by dv, all right, ds by dv at constant temperature, dp by dt at constant volume, dp by dt at constant volume. Okay, so this one is correct, and sign is we are right, this basically this is the sign. Okay, and this is the sign. So basically it's ds by dv at constant temperature, dp by dt at constant volume, and these two signs are same. Okay, like this and like this. Okay, so that means this should be positive. So C is absolutely incorrect answer. Okay, next is ds by dp at constant temperature, ds by dp at constant temperature, all right, dv by dt at constant pressure, and sign are basically opposite. Okay, so there should be a negative. So correct answer over here is B and C, right? So B is basically incorrect option and C is basically incorrect option. So correct answers are B and C. Okay, is it clear to all of you? Any doubts to anyone? Fine. Okay, I hope this one is clear. Alright, so D and C. So let's solve this question. So the question is, which of the following is not correct for an ideal gas? Okay. So first statement is del U by del V at constant temperature. Now we know this comes from first law of thermodynamics. Okay. So now what is first law of thermodynamics, or we can say it comes from your first equation of thermodynamics. Okay. So basically del U by del V at constant temperature is temperature del P by del T at constant, right? Basically volume, and minus pressure. Okay, so this is the term. Next thing is we have to find this for an ideal gas. Okay, so we know PV is equals to nRT. Okay, if PV is equals to nRT, so we have to find del P by del T. Okay, so P is basically P nRT by V. Okay, so now del P at del T at constant volume is nothing but nRT. Okay, so is it clear to all of you? You have to differentiate it with respect to temperature. Okay, so this is nothing but nr by v. Now this temperature is nRT by v. Okay, minus pressure. So now we know nRT by v is nothing but pressure, so pressure minus pressure is equals to 0. So this option A is absolutely correct. Okay, for ideal gases, del U by del V at constant temperature is 0. Okay, you can learn this thing directly. There is no need to solve this way, but this is the correct way. If let's suppose, right, you forget an examination, so you can just definitely you can just quickly solve this particular definition. Okay, now let's take next option. So next option is basically del H by del P at constant temperature. Okay, this is again thermodynamics second equation of state. So now we have del H by del P at constant temperature is equals to volume minus temperature dV by dt at constant pressure. Okay, so we have to find this thing for ideal gas. So PV is equals to nRT. So with respect to volume, right? So volume is nRT by P. So del V by del T at constant pressure is nothing but nR by P. Okay, now if I write volume minus nR by P, so it's nothing but again volume. Okay, so volume minus volume is equals to 0. So for ideal gases, del H by del P at constant temperature is equals to 0. Okay, so this is 0. Now let's go to third option. Now what is this third option? Okay, this is different from these two options. So this particular thing is nothing but your Joule-Thomson coefficient. Is it clear to all of you? It's nothing but Joule-Thomson coefficient. Okay. Now for ideal gases, generally Joule-Thomson coefficient is 0. Now which equation you have to learn for Joule-Thomson equation? So this is the very famous equation, that Joule-Thomson coefficient is nothing but basically 1 by Cp. Okay. Then you can write temperature into del V by del T at constant pressure minus volume. So this is the equation for your Joule-Thomson coefficient. Okay, now for an ideal gas we have to find this thing, and we just found out that this is nothing but volume, right? So this part is nothing but volume. So volume minus volume is 0. So 1 by Cp into 0 comes 0. Okay, so Joule-Thomson coefficient for ideal gas is basically 0. Okay, and this is the way to write Joule-Thomson coefficient. So basically change in temperature or temperature drop with respect to pressure at constant enthalpy is your Joule-Thomson coefficient. Okay, so we can write in this manner, and for ideal gases Joule-Thomson coefficient is 0. Okay, so option C is also correct. Now let's go to option D. Okay, let's go to option D. So this is your option D. So PV is equals to nRT for volume, for basically ideal gas, and we have to differentiate with respect to temperature. Okay, so PV is equals to nRT by V. Okay, now del P by del T at constant volume. Okay, so this is nothing but nR by V. So this is not 0, so we have to get 0, but this is some basic value. Okay, this is not equals to 0, so definitely option D is incorrect. Okay, so correct answer is option D. Right, because del P by del T at constant volume is not equals to 0, right? So is it clear to all of you? Any doubts to anyone? Fine. So generally what we say that Joule-Thomson reactions are basically right, it's your it's adiabatic, right? It's adiabatic and isoenthalpic. Right, it's adiabatic and isoenthalpic. Okay, so basically enthalpy is also constant, and the heat transfer is also constant. Okay, so correct answer is option D. A option is not clear to you. See, in A option we have to find del U by del V at constant temperature, and this comes from thermodynamic first equation of state. Okay, and this value is nothing but temperature del P by del T at constant volume minus pressure. Okay, so you can find for this, you can find that for ideal gases this value is equals to 0. All right, okay. So Carnot takes 90 joule of heat. Okay, so basically a Carnot takes 90 joule of heat from the source kept at 300 Kelvin. Okay, so Carnot cycle takes up your 90 joule of heat. That means T1, basically Q1 is your 90 joules, and Q2 you have to find, okay, and T1 is your 300 kelvins, okay. So Q1 is 90 joules and Q2 you have to find, and T1 is 300 kelvins, okay. So you have to find the correct statement among the following. So first option is it transfers 60 joule of heat, that means Q2 over here is 60 joules, and to the sink at 200 kelvins, that means T2 over here is 200 Kelvin, okay. Now we have to prove this thing that these values are correct, okay. So we know for this thing, we know for Carnot cycle the efficiency is nothing but 1 by T2 by T1, or we can write 1 by Q2 by Q1, okay. So this is your Carnot cycle's efficiency. 1 minus T2 by T1 is equals to 1 minus Q2 by Q1, okay. So we just have to equate these values because this is equals to your efficiency, okay. So 1 and 1 will be cancelled out, minus and minus will be cancelled out, so now you'll be left with T2 by T1 is equals to Q2 by Q1, okay. You just have to prove this thing that you are getting these two values are same, okay. So now if I put T2 is equals to basically 200 kelvins, okay. So T2 is 200 kelvin and T1, as I have written over here, it's 300, okay. So 200 by 300 is equals to Q2. Q2 is 60 joules, that is your heat of your sink, okay, right. And this Q1, which is of your source heat, basically it's your 90 joules, okay. So if you calculate, this is nothing but 2 by 3, okay, and if you calculate, this is nothing but 2 by 3, okay. So 2 by 3 is equals to 2 by 3, that means this information for your Carnot cycle is definitely correct, okay. So we don't have to solve B, C and D option because A is getting the correct answer, okay. Now let's suppose I have to prove that A is correct answer, okay. Let's go to option B. So in this case 50 by right 300, so basically right, it's your 200 by 300 is equals to 50 by 90, okay. So you can see this is 5 by 9 and this one is 2 by 3, okay. So they are not equal to each other, so we'll go with option A, right. So is it clear to all of you? Any doubts to anyone? Right, is it clear? Alright, okay. So all of you are getting 0 values for system, surroundings and for universe, okay. So let's calculate this question. So we know delta S is basically NCP, right? We can use NCP ln, and in place of V1 V2 V2 by V1 we can use P1 by P2, okay. So this is your equation plus nr, right, ln t2 by t1. So this is the equation, okay. So now I am giving you some hint, since all of you are just giving me the incorrect answers, right? So now this question is basically your homework, okay. And your delta S system is not equals to 0, okay. You can calculate delta H system. Delta S surrounding for, right, adiabatic process is definitely equal to 0 because there is no heat transfer, but delta S system is not equals to 0, okay. Now if I want to calculate delta S universe, so this will be equal to delta S system plus delta S surroundings, okay. Now we know that delta S surrounding is equals to 0, so that means delta S universe is equals to delta S surrounding, okay. So this is your hint for this question. I hope this much hint is enough, okay. So you just have to use this equation, and how you can just use these temperature equations, and this is the equation, right? We have P1 and P2. We can find Cp for monatomic gas. You can use this equation. You can find out delta S of system, right? And using this particular value, you can calculate delta S of universe, which is nothing but equal to delta S of system, right? Yes, Ankit and Saleja, definitely, right? So you're getting some value. So this is how you have to calculate it, and that value will be equals to delta S of surroundings. Okay. So is it clear to all of you? Any doubts? Okay, can you do this problem now? So I've given you enough hints, right? And you have answers also. So now you can relate with this information and you can find out the correct answer. Okay. So just figure out what mistake you were doing in this question. Okay. So let's take next question. All right, Uday. So you just do one thing. In the description box, you'll find the link of my profile. Okay. So just click to that link. You'll find a message box. Okay. So you can drop your queries over there. I'll definitely respond to your query. Okay. So how you have to start your preparation, and from which particular courses, right? And how you have to follow your preparation, I'll definitely tell you over there, right? So you can message me on my profile. Alright guys, so what's the correct answer? You first try, okay, Anuradha, first try your best, first give it this question a best shot, then only we'll discuss this answer. Yes, Sudha, I got your message. I'll get back to you on this, okay? Alright, so 30 more seconds for this question. Okay, everyone. So please, let's understand this question. Okay. So the question is, first of all, what's the question is saying? Basically, the question is a liquid which is confined inside an adiabatic piston. Okay. See, let's see how we can just take right help from these small points. Okay. First of all, they are using this term liquid. That means your system is liquid, not gas. Okay. And we know this term, that is gamma. Okay, what is gamma? Gamma is nothing but ratio of Cp by Cv. Okay, this is your gamma. Gamma is nothing but ratio of Cp by Cv. Okay, and we know that Cp and Cv or gamma is basically defined for gaseous molecules. Am I correct on this? Right, just confirm this thing if you are clear on this aspect, that gamma is defined for gaseous molecule, not for liquids and not for solids. Okay, so whenever we are taking gaseous molecules into consideration or our system is gaseous, then only we can define gamma. Okay, so with this information, what I can do, I can cancel option A and option B. Okay, so now I have increased my chances of getting to the correct answer. So now it's like 50-50%. Okay, either option C is your correct answer or option D is your correct answer. Okay, now I just have to confirm if option C is correct or not. Okay, so now let's solve this question. So we have cancelled out two options. Right now we have only two options left. Okay, so next thing is a liquid which is confined inside an adiabatic piston. So this is your adiabatic process. Okay, if this is your adiabatic process, so Q must be 0. Okay, next is suddenly taken from state 1 to state 2 by a single step process or by a single stage process. This sentence, you can just read this sentence again, suddenly taken from state 1 to state 2 by a single stage process. So can I say this process is irreversible? Right, they have given you enough hints, single stage process or suddenly taken from stage 1 to stage 2. Okay, so this process is your irreversible process. Okay, so we got two information with two statements. Okay, next is if the piston comes to rest at point 2 as shown, so that means this is your final position and this is your initial position. Okay, then the enthalpy change for the process will be, so you have to calculate the enthalpy change. Okay, so let's solve this question. So first of all, we'll be definitely using first law of thermodynamics. Okay, we know from first law of thermodynamics we have delta H is equals to, right, delta U plus W, or what we can write down, we can write down basically delta U is Q plus W. Let's go with this equation. Okay, so delta U is Q plus W. This is your first law of thermodynamics. Okay, now if this is the law and the process is adiabatic, so Q is equals to 0. Fine. If Q is equals to 0, so what I can write, that delta U is equals to work done. Okay, so we got first relation. Okay, we got first relation. Next thing is, right, next relation is basically, we know delta H is delta U plus delta PV. Okay, we have this second relation. So from this first relation, we have delta U is equals to W. So that means delta H is equals to W plus delta of PV. Okay, so is it clear? So we got our second relation. All right, so now what we have to find, we have to find out enthalpy change. That means this value we have to find out. Now if somehow I can manage to find W or change of this delta PV, so I can definitely get to the correct answer. Okay, so now let's solve this equation. Next is, first task is we have to calculate the work done. Okay, now how you can calculate the work done? This is irreversible process, so definitely work done is minus P external V2 minus V1. Okay, work done is minus P external V2 minus right, V1. So now what is P external? This is your final process, so that means P naught is your P external. So minus P naught, V2 is 4 V naught and V1 is V naught. Okay, so it's 3 V naught. Fine. So work is basically minus 3 P naught V naught. So this is your work done, minus 3 P naught and V naught. Okay, so we got our work done, that is minus 3 P naught V naught. Next is we have to calculate this change of pressure volume. Okay, so let's calculate this change. So this is P2 V2 minus P1 V1 or P final V final minus P initial V initial. Okay, what is P2? P2 is P naught, right, and V2 is 4 V naught. Okay, what is P1? P1 is 2 P naught and V1 is V naught. Okay, so basically 4 P naught V naught minus 2 P naught V naught is equals to 2 P naught V naught. Okay, so this is the change, 2 P naught V naught. Okay, so this value is 2 P naught V naught. Now you can just use this calculation. Delta H is minus 3 P naught V naught plus 2 P naught V naught is equals to minus P naught V naught. Okay, just we have used basic equations and applications. Okay, although the statement is little tricky, it's not tricky, you just have to understand step by step. Okay, so correct answer is option C, that enthalpy change is defined by minus of P naught and V naught. Okay, so is it clear to all of you? Any doubts? Fine, I hope this question is clear. This is not a right difficult question, it's just that you have to be calm in this question, right, and you have to go step by step. Okay, and this will only come if you are practicing a lot of questions. Okay, so I think we have right few more questions, so let's complete these questions. Okay, let's complete this question. So this is the next question. Alright, okay. So let's solve this question. So question is Gibbs free energy of mixing is denoted as delta G mix. Okay. Right, and what's given? 1 mole of helium. So basically you have 1 mole for helium and you have 3 moles for neon and you have 2 moles for argon. Okay, are mixed at the same pressure and temperature. Assuming ideal gas behavior, the value of delta G mix by RT. So you have to calculate this value of delta G mix by RT, right? So we know the formula of delta G mix. So delta G mix is nothing but RT summation of Ni ln Xi, right? Where R is your universal gas constant, T is temperature, N is number of moles, and Xi is your mole fraction. Okay, so what can I write? That delta G mix is basically delta G for helium plus delta G for neon plus delta G for argon. Okay, so if I take this expression, so RT would be common. So what I can write? 1 mole for helium ln Xi, right? So 1 by, and total moles is basically 6. Okay, so 1 by 6 plus basically we have 3, 1 by, right, 3 by 6 plus we have 2 ln 2 by 6. Okay, now you just have to calculate this equation. R will be 8.314 and temperature will be room temperature. Okay, so basically you can take this temperature value. Okay, so you have to find out delta G mix by RT. So you can take this to the left hand side. Okay, you can take this to the left hand side and the equation would be very simple. Okay, so delta G mix, so delta G mix by RT is equals to this value. Fine. So now this is how you have to calculate it, right? So the best way is you can use the calculators. Otherwise, what you can do, you can write this way: 1 by 6, 1, right? Ln 1 by 2, basically 3, and 2, 1 by 3, 2. Okay, this way also you can write down. Now you can use the product rule. So 1 by 6 into 1 by 2 whole cube into 1 by 3 whole square, and you can find this value, then you can take ln of this term. Okay, so this is how you can calculate it. So just you need to just multiply the values. Okay, so if you multiply the values and you just substitute the values, you'll be getting the correct answer. Okay, so is it clear to all of you? Is this point clear? Okay, so this is how you can get this question correct. Okay, so I hope this is clear. So this is all about this session. Okay, so we have one more session tomorrow and we'll be discussing more questions with thermochemistry questions, right? So we'll be taking thermochemistry questions in the next session. Okay, so this is all about this class. So hope you found these questions useful. So we have covered already 3 lessons on thermodynamics. Okay, so you can just watch all these 3 lessons. Two of them are basically available on Unacademy special platform and one is on YouTube. Okay, so you can check out those lessons also if you want a quick revision of thermodynamics. Okay, so I'll see you in the next class. Take care everyone. Bye bye.